The demand of energy has never been greater. All over the world, people struggle to survive without electricity. Over a billion people across the world have no access to electricity, out of which 500 million are in Asia. Coming over to Pakistan, there are some areas which are difficult to put on grid. Our project, which is fabrication of water turbine for slow-moving water, focuses on this very issue. If we look at the water, which is 830 times more powerful than air at the same speed, we need only few miles an hour to extract tremendous amount of energy that's within that flow, and of course 70% of the planet is moving water. Hydropower supplies 16% of the total energy, but dams require large-scale investment and need to be connected to grid to distribute power. Most of the water that is running on this planet is below 6 miles an hour. This is the source of energy which is plentiful and accessible, and technologies have been created and are being improved to take advantage from this source of energy. Slow-moving water potential has been difficult to capture because the momentum behind water that is been flowing down the river has been difficult to turn the turbine. Achieving success is little difficult in making these kind of turbines. Various bladed technologies like turbines, Darius, Savonius require a specific cut-in speed to generate meaningful amount of electricity. The design we selected to work on was lift-based turbine. For the proof of concept, we started off by limiting our diameter to 0.6096 meter, which is 2 feet, and with the help of equation for required power, which includes the efficiency of generator, required power was calculated. And furthermore, blade element momentum theory was used to find out axial and tangential induction factor, which helps in finding the core length for selected parameters. Core length would eventually lead to Reynolds number, which comes out to be in the range of laminar flow. With literature review, 4 most suitable profiles were selected, and the one covering the most area under the curve was selected, which was S822 profile. Core length was divided into 10 sections, and twist angle for each section was calculated. Rotor was designed in SolidWorks, and calculated twist angle at each section was given to blade, and after that rotor was set to simulations. Pressure controls, velocity vectors, and solidity impact helped in selecting the number of blades for fabrication, and the number selected was 3 because it gives maximum rotational velocity as compared to other. Rotor was fabricated with 3D printing, and the material selected was PLA. Rotor was assembled with generator, which has the capacity to generate electricity at slow rotational speed of shaft, and rectifier was used to convert AC output of generator into DC to light up the LEDs. Testing of turbine was done at Mora Muradu Stupa, which was at KPK, Pakistan. The water speed was approximately 0.9 meter per second and successfully lighted up the LEDs, which in combined were of 25 watts. Error calculated was 37.5%. Because the flow available was turbulent, and the Reynolds number on this turbine was in the range of laminar flow. Thank you.